So we have two more topics left to cover for chemical reactions and quantities. So a lot of segments for this. It's a big piece of the semester. It's probably taken us a few weeks to get through it all. The next topic we're going to look at for reactions is limiting reagent. So limiting reagent builds off of stoichiometry, and it comes to the idea that we're going to use up all of one of our reagents before we use up all of the other. So for instance, if you were given 1 dozen loaves of bread, a gallon of mustard, and 3 pieces of salami, how many salami sandwiches can you make? And obviously, if you only have a few pieces of salami, then that's going to limit how many sandwiches you can make. You'll have plenty of bread left over and plenty of mustard left over. And that's just it is. The limiting reagent is the reactant that you run out of first. Okay, so if I take two things and I'm putting them together, one of them inevitably is going to get used up before the other. The one that gets used up first is the limiting reagent, and anything that's left over would be excess reagents. Okay, so the limiting reagent is literally determining how much product you can make. So how do you figure out which one is going to be your limiting reagent? Well, you're going to have to do multiple stoichiometry problems. So the one that makes the least amount of product would be your limiting reagent. So let's look at an example question from an old exam. Copper reacts with sulfur to form copper 1 sulfide. If 10.6 grams of copper reacts with 3.83 grams of sulfur, how much product will be formed? So again, I told you way back in the beginning that chemistry is a building piece where you keep building off of each chapter, and here we go. This is definitely a summation type of problem where we're going to be tackling several different topics that we've already talked about. First off, we see naming. Right? So for naming, you have to be able to come up with the pieces here. So if 10.6 grams of copper reacts with 3.83 grams of sulfur, how many grams of product will be formed? And of course, the product in this case is going to be copper 1 sulfide. So you have to do the naming in order to figure out what the product's going to be. So we're going to start with a balanced chemical equation. So we're going to take copper plus sulfur. We're going to make copper 1 sulfide, which works out to be Cu2S. Now, if you didn't get that formula correct, then there's no way you'd get the balancing correct because now you need 2 coppers for every sulfur. Now, once we've gotten to that step complete, we've got the balanced chemical equation, and we're finally ready to put together some math components. So I'm going to start with the copper since that's the first number. We've got 10.6 grams of copper. So what we're going to do is figure out how much copper 1 sulfide we can make from 10.6 grams of copper. So the first thing we'll do is the first step in our 3-step process. We'll use our periodic table to calculate how many moles of copper we would make. Once we have moles of copper, we're going to calculate how many moles of copper 1 sulfide would we make. And here it's going to take us 2 moles of copper to make 1 mole of product. And then last but not least, we're going to calculate how many grams of product would we make based upon the periodic table of 159.16 grams of product. That works out to be 13.3 grams. So what we figured out so far is that if we use just the 10.6 grams and we had an unlimited amount of sulfur, we would make 13.3 grams of product. Next, I'm going to do just the opposite. I'm going to start with the 3.83 grams of sulfur, and I'm going to assume that I have unlimited amount of copper. So now, based on the sulfur, it's going to be 32.06 grams for every mole of sulfur, coming from the periodic table again. Then we're going to use the balanced chemical equation, and we see that it's going to be 1 to 1. So for every 1 mole of sulfur, we'll make 1 mole of product. Our last step here is going to look exactly the same because we want to look for the same product. And so that's going to be 159.16 grams for every mole of product. Now when I run these through my calculator, it gives me 19 grams of copper product. Now, the limiting reagent is the one that's going to make the least amount of product. So that means the 13.3 grams is smaller than the 19 grams, thus copper is our limiting reagent. Now the question could have been how many grams of product would be formed, and it could have just stopped there, or it could have been what is the limiting reagent. Okay, either way, you'd have to go through all these steps to answer either one of those questions. All right, so here we go. Another old test question. If I have 10.1 grams of magnesium and I react it with 2.87 grams of HCl, how many grams of magnesium product are going to be formed? All right, so the first thing we need is what? A chemical reaction. So that's going to be magnesium plus HCl goes to magnesium chloride plus H2. What do I need next? I'm going to have to balance that, right? So it's going to be 2 HCl to make that happen. The next thing I'm going to do is figure out my magnesium. It's going to be a 3-step process. I'm going to take 10.1 grams of magnesium. I'm going to convert that to moles of magnesium using my periodic table. Magnesium grams will cancel out. Then I'm going to use my balanced chemical equation to balance moles of A to moles of B. Moles of magnesium will cancel out. And then last but not least, I'll turn that into mass of product. And my moles of magnesium chloride will cancel out. So based on the 10.1 grams of magnesium, we're going to make 39.6 grams of magnesium chloride. Now I'm going to take the HCl, 2.87 grams of HCl, 3-step process again. I'm going to convert that to moles of HCl. Grams will cancel out. Then I'm going to get into moles of product. Moles of HCl will cancel out. Last but not least, the third step will look exactly the same, mass of magnesium chloride. Moles of magnesium chloride will cancel out, and now I have 3.76 grams. So how many grams of solid were formed? Was it the 3.75 grams or the 39.6? It's always going to be the smaller value for our product, which means it's going to be 3.75 grams. Now for fun, you can try to figure out how much excess reagent remains. So I'd be happy to help you with that one. Get a hold of me if you want to work that out, and we'll see what you can do. All right, let's check out a second one here. If 10.3 grams of aluminum reacted with 51.7 grams of copper sulfate, how much copper will be produced? See if I can get the pen to work. See if that works. All right. So if 10.3 grams of aluminum reacted with 51.7 grams of copper sulfate, how much copper will be produced? So again, we'll start with 10.3 grams of aluminum. That's going to be a 3-step process. First thing I'm going to do is get into moles of aluminum. So I'm going to put 1 mole of aluminum on top. Then I'm going to convert my moles of aluminum to moles of what? Well, we want to know how much copper will be produced. So this is going to be moles of copper over moles of aluminum. And last but not least, I'm going to convert my moles of copper into grams. All right. So this one I can find from the periodic table. So according to the periodic table, I believe aluminum is 26.98 grams. All right, now I need a balanced chemical. Wait a minute, we didn't balance a chemical equation. I wonder how many of you at home were going, Mr. Caro, you didn't do the equation. You need the equation. I hope it was all of you. If not, at this point we realize we need that balanced chemical equation, so let's go ahead and put that together. Aluminum is going to be reacted with copper sulfate, CuSO4. We know we're making copper, which means probably the aluminum is going to kick this out, right? This looks like a single replacement reaction. Notice you had to know that, and there was nothing in the question that was telling us that, but we have a single metal, we have a compound, the metal is going to kick the metal out, so copper will now be by itself, and we're going to make aluminum sulfate. Aluminum is a +3, sulfate's a -2, we'll crisscross those, that's going to be Al2, SO4, 3 times. All right, now that we have all of our compounds and formulas in here correctly, now we need to balance it. So we're going to need 3 sulfates. So I'm going to put a 3 in front of the copper. We're going to need 2 aluminums. So I'll put a 2 in front of the aluminum. Since we have 3 copper sulfates in the beginning, we're going to need to make 3 coppers in the end. And there's our balanced chemical equation. So now we can see we're going to have 2 moles of aluminum is going to make 3 moles of copper. And then for my last step, I'm going to go back to the periodic table, and copper has a mass of 63.55 grams. All right, now we're ready to run that calculation. So I'm going to grab a calculator. We have 10.3 divided by 26.98. Multiply that by 3, divide by 2. Then we're going to multiply that by 63.55. And that gives us 36.39. So we're going to round that up. We're going to have 36.4 grams. Now that's how much product we would make based upon the aluminum. Next, we're going to take the copper sulfate and we're going to do the same thing. So we're going to do 51.7 grams. This time it's going to be CuSO4. Still going to be 3 steps. And here we know the last step needs to be the same. We want to make sure we're going to the same product. So I'm going to go ahead and write the 63.55 grams in for the 1 mole of copper right away. Now that means I know I need to get into moles of copper here. We know by the balanced chemical equation that's going to be 3. So that's going to be 3 moles of copper. And we know it's going to take 3 moles of copper sulfate to make that happen. So that's going to be 3 moles of copper sulfate. All right, so in the beginning here, we're going to need to get to moles of copper sulfate. So that's going to be 1 mole of copper sulfate. And now we need to put together a mass. So I'm going to go to my periodic table. Copper we know is 63.55. Sulfur is 32.07. Oh, 6. That was close. Plus 32.06. Plus we have 4 oxygens at 16 each. That's going to be 64. So we have a molar mass here of 159.61 grams. All right, so now we're ready to run this through. We're going to do 51.7 divided by 159.61 times 3 divided by 3 times 63.55. And according to this equation, we're going to make 20.6 grams. And so again, this would be our final answer. So if this much aluminum reacted with this much copper sulfate, we would make 20.6 grams of copper. All right. Hopefully these things are going well for you. You're figuring them all out. If not, again, come to an office hour or student hour or schedule time with your tutor or make an appointment with me. Make sure you're getting the help you need. Don't get frustrated with it as much, try to avoid the frustration as much as you can. There's plenty of resources here, people who are willing to help you. So take advantage of that. Even though it's online, that doesn't mean you can't see people face to face to get help, or at least on a Zoom. For instance, you can easily make an appointment with me. I can meet you on Zoom. I believe the tutoring center is open as of today anyway. It's open live. You just have to make appointments and follow a certain protocol. All right. This ends with the last question of how much excess reagent will remain. Again, I'm going to leave that for you to do. I don't actually ask that question on exams, so it's a good practice question to see if you're understanding all of the topics. At the same time, you're not going to be held responsible for having to know how to do it. So if it is something that's kind of bugging you and you want to know how to do it, or you want to see it done, or you just want to double check your answer, again, just shoot me an email, set up an appointment, one of the two, or come to a student office hour. All right. Moving on to our last topic, we're going to finish it up in this section. We have energy and chemical reactions. How much energy, and then whether it's going into the system or out of the system. So energy, if you remember, we measure in joules or calories, right? And every reaction is going to have some sort of energy associated with it. If you recall, when we talked about catalysts, I showed you an energy diagram. That particular reaction was exothermic, and exothermic means it's going to release energy. So that means our products are going to be less energetic than our reactants. So when the reactants reacted, they made more stable products and released that energy. Endothermic reactions are quite the opposite. They're going to absorb energy. And so the products then are going to be more energy than the reactants. And so we're going to call that endothermic. It's going to cost us energy to make those products. Now, regardless of whether it's endothermic or exothermic, we have to remember that energy is stored in bonds. If you remember, I talked about the wooden balls and the springs making bonds, and we talked about kinetic versus potential energy. And energy in a bond is potential because it's a stored energy. All right, so let's take a look at a reaction and see how this is going to work. So here we're going to take carbon, we're going to react it with O2 to form CO2. So this is a combustion reaction. You don't have to worry about the actual values here, but I have a book in the lab called the CRC for Chemistry Handbook. It's going to give you thermodynamic quantities for these things, and so we could actually put a value, an energetic value on them. Now the reaction is going to take place, and it's going to turn out that it's exothermic. And so CO2 is going to be a product, and the product is more stable than the reactant. I can also look up the value of the CO2, and that means we're going to have a difference here. And as it turns out, that difference is 395 kilojoules. Now again, don't worry about where I'm getting this number from. This is something I would tell you on the test. Okay, I would say this is an exothermic reaction and you can release 395 kilojoules of energy in this reaction. What I need you to know is, what does that mean as far as our chemical reaction itself? Well, if it's exothermic, then that means energy is a product. And so if I were going to rewrite the chemical equation, I would add 395 kilojoules to this. So now what this is telling me is for every 1 mole of carbon that combusts with 1 mole of oxygen, I'm going to form 1 mole of CO2, and it's going to release 395 kilojoules of energy. Now, in terms of bonds, what does that mean? Well, that means I'm breaking apart the oxygen. That's going to require energy. Okay. Then I'm going to take those oxygens and connect them to the carbon. That's going to give us energy back. In this case, the energy that we're getting back from the making of those bonds is more than the energy that it costs to break the O2 bond. And so that's going to be an exothermic reaction. The products here are lower in energy than the reactants. The reaction is said to release energy. Okay, that's all I'm asking you guys to know about this. So if we have an exothermic reaction, the energy will be a product, and then the products are more stable, less energetic than the reactants. Okay. Now, another one would be this. We have calcium carbonate, decomposes to form calcium oxide and CO2. And this time, calcium oxide and CO2 are going to be higher in energy than our reactants, our calcium carbonate. When the reaction takes place, again, I can use my text, the CRC textbook, to figure out what these values are, but there's going to be a difference here of 176 kilojoules. Now, this time, it's going to cost us 176 kilojoules. So what will that look like as far as the reaction goes? Well, now I'm going to rewrite it so that calcium carbonate will require 176 kilojoules to produce calcium oxide and CO2. Since I'm putting energy in the reactant side, this is going to be an endothermic reaction. The products here are higher in energy than the reactants, which means the reaction is going to absorb energy. Now we can take this thermodynamic idea and we can put this back into stoichiometry. Since the chemistry happens in moles, what we can do is write an equation that includes energy. We call this a thermochemical equation. Again, this is something else I would get from the CRC book. It's not something I would expect you to know. You can take methane, combust it with oxygen. You'll need 2 O2s. It'll produce a CO2 and 2 waters, along with 802.2 kilojoules of heat. So 1 mole of CH4 then makes 802.2 kilojoules of energy. When you make 802.2 kilojoules, you make 2 moles of water. That reaction would be written out like that. And now I could ask a question relating to energy. If 10.3 grams of methane are burned completely, how much heat will be produced? So we'll set this up just like we did before with stoichiometry problems. We'll start with 10.3 grams of methane, and we'll convert that to moles of methane. I'll go to my periodic table, and for every 1 mole of methane, it's going to be 16.05 grams of methane. Here's where it changes a little bit. The stoichiometric ratio is going to give us the answer. So we don't have to convert A to B and then solve B to a mass, because now we're looking at energy. So instead, what we're going to do is we're going to say we have 1 mole of methane is going to give us 802.2 kilojoules of heat. We run that through our calculator and we get 515 kilojoules. So if we burn 10.3 grams of methane, we will burn off 5.15 kilojoules of heat. So that's it. Again, I wouldn't expect too much thermochemistry on your test. Typically, the questions that are asked have everything to do with endothermic and exothermic, and whether the value is going to go into the reactant or the product side. So make sure you understand those concepts. Typically, the math that comes with this chapter are stoichiometric and limiting reagent questions. I will also post a Word document up that gives you some more stoichiometry problems that are old test questions that I would use or have used in the past, along with some answers and where I can, and other ones I might not be able to get the answer to you posted up in time. That feel free to, like, again, stop in, make an appointment with me, and we can go over it via a Zoom session. All right, that ends our chapter, and so we'll be moving on now to gases.